So I wanted to finish chapter 6 by covering stable isotopes. This is just going to be a quick introduction, really just one example of how stable isotopes are used, but they are great tools as tracers in environmental and geological studies. And so what we can do with these stable isotopes is follow certain physical, biological, and chemical processes. And we can do that by measuring isotopic ratios. Because what happens in these specific processes, it's very slight, but given the process, we will get fractionation. Fractionation is where the process prefers one isotope or over the other. Most of the time, the process prefers the lighter isotope. You can think of, say, a chemical reaction. The chemical reaction, say, denitrification, is turning over nitrate with CH2O and converting it to nitrogen gas. It's going at a certain rate. It's a reaction. You could imagine that that reaction would go slightly faster if the nitrogen was a slightly lighter. And so because of that, say for denitrification, it will process nitrogen 14 faster, very slightly, but faster than nitrogen 15 that we would find in, say, nitrate. So over time, you get this fractionation and it can be measured. All processes have a different way of fractionating. Therefore, you can use that information to figure out a source of, say, a certain carbon or nitrogen or oxygen. So for our example, let's consider evaporation and how it fractionates oxygen isotopes in water. So let's look at water and the two highest abundant combinations of hydrogen and oxygen isotopes. Remember, hydrogen could also be as deuterium, H2. That is a stable isotope, but we're not going to consider those combinations. The two combinations we're going to consider is H1 with either oxygen 16, which is very prevalent, or oxygen 18. When we consider the abundances of these two types of water, we see that it's 1 to 500. So there's much more oxygen 16 associated water than oxygen 18. So let's put this into the process of evaporation. Say we're at the equator where it's nice and warm and we're getting a lot of evaporation. Well, you can imagine when those photons from the sun hit the surface of the ocean that these molecules are just about ready to leave the surface. And so they need that extra little energy and they will go from liquid water to gaseous water. And we can also imagine that if we have these two different weights of water, that the water with oxygen 16 will be moving faster. And this is just based upon an equation for kinetic energy. Both of these water molecules will have the same kinetic energy. But in doing so, that means that the lighter one will have a higher velocity. And so what we get then is a fractionation of the oxygen isotopes where we actually get more oxygen 16 to go into the vapor phase. So this is the premise for many conclusions that we're going to make, or I should say inferences for past climates, actually. So this is the beginning of starting to think about fractionation in the ice sheets and in the oceans, and using dated marine sediments to start to put a picture of the past together using oxygen isotopes. So let's consider the first idea, knowing that we get fractionation from evaporation. So when the Earth's climate is cold, there's going to be more water locked up into the ice sheets, and that makes sense. And so this water in the ice sheets is enriched with oxygen 16. And that's because it's from the process of evaporation. That evaporated water condenses, it moves towards the poles, and then it precipitates and in the form of ice and gets locked in those ice sheets. So that reservoir of water contains a lot of oxygen 16. So what that means to us then is that the oxygen 18 to oxygen 16 ratio goes up in the oceans during this time. And also we could say too that the Earth's climate in when it's warm, that the ratio goes down in the ocean. So as I mentioned about a minute ago, is we're going to use marine sediments to monitor these oxygen isotopes, because we've dated the marine sediments. So now we can use this as a tool, a proxy, to determine past climates. And the way we're going to do that is by using forams. So these are small organisms that use calcium carbonate to form their exoskeleton. This calcium carbonate contains oxygen that is from the ocean. And so we're going to be able to date the marine sediments using radioactive isotopes like thorium-230, which we've done an example with that in the previous worksheet. And once we've dated the marine sediment, then we can start picking through the sediments and finding forams at different depths and analyzing the oxygen 18 to oxygen 16 ratio within their skeletal remains. And from that, we will be able to piece together a picture of past climates. Because again, this ratio is affected by how much of the water is locked up in the ice sheets. That takes away the oxygen 16, changes this ratio, and so this ratio, what we'll find, is greater in colder climate conditions and lower in warmer climate conditions. And so because the fractionation is so small, the way we measure it is by using this delta notation. And so the delta, what it is we measure the isotopic ratio of the sample, we subtract the isotopic ratio of a standard divided by that same isotopic ratio of the standard times 1,000. And that gives us a numerical amount. So these standards, you purchase them, they cost a lot of money, but what they allow us to do is no matter who's doing the research, we're all using the same standard, and that's very important. And so the most common one is this SMAU, which is standard mean ocean water. And so again, you purchase it and it's distributed all over the world. All scientists are using it, therefore they can relate their values with other labs. There's other standards though as well, and you can relate standard to standard. That's not a problem. But there's also Vienna, SMO, and there's some SLAP, some standard light Antarctic precipitation. And once in a while they have to renew these standards, but again, everybody's using them and it's necessary for this sort of field. And so here are some of the standards for some of the different elements. And this is a table from your textbook. So last, I just wanted to mention too that we use these oxygen isotopes in marine sediments to look at past climates. We can also do similar measurements in ice core sheets. So once we've actually dated the ice core, we then can see that higher temperatures lead to a less negative delta 18, or lower temperatures leading to a more negative delta 18 for oxygen. And so delta, again, whether it's more or less negative, it's all relative, but it does have meaning given that everybody's using the same standard. So this is from Greenland here. Here is a profile, and these values here are showing the delta for oxygen 18. And so what we see is a less negative, or I should say a more negative delta. This is showing the last ice age. And what we see with less negative delta for oxygen 18, we see the warming that has occurred since the last ice age. And so we can go on and on with this topic. And so I just want you to look in your textbook, look at some of the different elements that also contain information upon fractionation. We see for nitrogen how the delta for nitrogen 15 changes with respect to sources and with respect to processes. And so this is useful information in tracking and tracing different sources within the environment. We can also do it with carbon because, again, different sources of carbon have a different fractionation. Even plants, different types of plants have different fractionation. There is a short mention of wheat and corn and how they fractionate CO2, carbon and CO2, carbon-13 differently. And therefore, you can look at, say, human remains, look at the carbon-13 fractionation and determine what they were eating thousands of years ago, just by looking at the stable isotopes. So there's a lot of interesting things you can do with this, and it pertains to all different elements on the periodic table. So please spend a couple hours looking at the textbook. I hope you enjoyed this video,